I'll go through the second part of lab 4, and after that I'll be checking off lab 4's week 1. So before I start, is everyone clear with lab 4 week 1? Like, is everyone able to understand what it is about? Did everyone build at least something that can, cycle through 0 to 9? Or do you have any problems with it?
I think something that I was struggling with is how do we create an exhaustive test bench when it's continually that the output is continually updating.
So, so the way I would deal with testing this particular version is, uh, like I would want, ideally to go from any state to any state that I can, right? So, uh, if I hit stop or start in each individual number that I am in, I should be able to do that flawlessly. So the way I would test it is have a stop signal go off for each of the numbers, and then wait for certain time period. This time can be anything, because if it works for certain durations, it is more than likely to work for others. So I will wait for some time, and then resume it again, because we have a stop signal. And then I will also check for a condition where I can jump from any state into the zero state. So I would again go from 0 to, 1 to 0, 2 to 0, and so on. And I would make sure my test bench gives these particular signals in order. So you can either go with a for loop, which will basically give, uh, after certain amount of time, or at every, you know positive. So since you are changing at every positive edge, you can actually get the values at every negative edge. So if you write something like always at neg edge clock, give me this value or display this value, then you should be able to get that thing. So I would actually go with that route. Does that help, or is there anything more than that?
I think it helps a little bit. I think I just have to maybe look at what I have with you and go over that.
All right, all right. Okay, so does anyone else have any questions with week 1? Because it is quite important for you to understand what week 1 is. And then because of that, you should, you'll be using that multiple times in this lab. So, okay, I have a question. So one thing to remember is, in the design that you're trying to do, you are essentially not having an input called D at all, because that input is basically an internal signal in the feedback loop for your particular flip flop. So give me 1 second. All right. So if you have uh, a flip flop something like this, so your traditional way would be to have a D input, Q output, and a clock here, right? But in this case, for our particular design, the D is basically being fed back by an adder with one tick B1, right? So this is what your flip flop looks like. So this is still a flip flop. This is your adder circuit with which adds 1 bit every time. So ideally, you will have a stop signal that goes into a flip flop, or that goes into your design in general, that will basically push, or a reset signal that will push your flip flop into 0000 state every time you hit that particular signal or something like that. So you need not actually worry about the D part, because essentially your main function would be Q is equal to Q plus 1. So this Q plus 1 part is being taken care by this particular module, and this non-blocking assignment of this will be taken care of by this flip-flop. Does that make sense? Does that help? Or do you have any more confusion over this? Yes, not in the beginning, but something like once your always block starts, you can always say that if there is pause edge of reset, or if there is, if your reset is high, if you are checking for the positive edge condition, if your reset is high, then Q is equal to 0, else you have Q is equal to Q plus 1, something like this. So whenever you hit reset, you'll obviously go into the 0th state, and you keep on doing that every time. I mean, because you also have a stop signal, you want to incorporate that stop signal somewhere inside this. So except for the reset condition, you can always say else if stop is equal to 1 or stop is equal to 0, depending on how your push button is performing. If stop is equal to 0, then also go to, instead of doing Q is equal to Q plus 1, you'll again go to Q is equal to 0 if stop is equal to 0 or stop is equal to 1, and then else you have Q is equal to Q plus 1, something like that. Like I'm talking at a very high level, but does that make sense? Do you understand what I'm trying to say? All right. So does anyone else have any questions? No? Yes? All right. So I'm assuming everyone is clear with that part, with the week one part. So I'll be checking that off once we are done with today's explanation. So what we'll do today is we'll try to understand how a clock divider works, or what a clock divider is in general. So what we'll do is we will get to a point where we'll use the same kind of similar module where we are counting different things, and then from there we'll understand what a clock divider is and how things are, stuff like that. All right. So what we'll do is we'll start off with something very similar, very familiar to us. That's the clock that we have always been using. So let's say we have a clock, right? And then it goes something like this, right? In general in general your clock's time period, or your clock's on and off periods, are in terms of picoseconds or nanoseconds or something like that. But for the ease of calculation, let's just say we have our clock to be off for 2 seconds and on for 2 seconds. So if given this situation, this clock keeps repeating itself between the time intervals. So this is your time period essentially. Similarly, this is your time period, and it keeps on repeating itself between these periods, right? So given this, the time period would basically be 2 seconds plus 2 seconds, that is your 4 seconds. Is that clear for everyone? Does everyone understand this part? uh okay, I just have one of them say yes. All right. So I'm assuming you do. So given this, now what would the frequency of this particular uh, what would the frequency of this particular clock be, or how would I calculate the frequency of this clock? Yes, that is 1 by t. So 1 by 4 seconds, which is 0.25 hertz, right? So this is your clock frequency in general, right? So if you have a clock, if you just do 1 by time period, you get the frequency of the clock. It is as simple as that. But there is a concept of clock division, or reducing the clock's frequency using certain hardware aspects. So before we get into that, let's see what your understanding is in terms of what clock division is. So when I say the term clock division, what do you guys think of it? Like, what do you understand from it? Like, what comes into your mind? Like, what is the process you're doing? So before you answer that, let me make some things clear. So when you divide a clock, you are essentially generating a new clock. So in this case, I'll call it clock new. So I'll generate a new clock. It is a clock that again goes from 0 to 1, but some other characteristics of this particular clock change, right? So so given this scenario, now what would clock division in general mean? Anyone?
You just need something to extend the period, like a counter or something.
That is true, but before we get to the counterpart, what I want to say is, by mentioning that I am dividing the clock, what I am doing is essentially dividing the frequency of the clock, or finding some way to reduce the frequency of the clock, right? So what this means is that because my frequency is 1 by t, it is clear that my frequency is inversely proportional to my time period, right? So whenever I say I'm reducing the frequency, that means I'm increasing the time period. So given this, uh, in the clock above, you have your time period to be 4 seconds, and that is defined by your on period and off period. So whenever I divide a clock, say I divide the clock by 2, that basically means I am doubling the time period, right? So I'm making the time period to be 8 seconds now. So the way I do it is what you are trying to design in this particular lab, right? So if I have a new clock, right, which is on for this amount of time and off for this amount of time, if I have a clock like that, right, so it is off for 4 seconds and on for 4 seconds, right? So something like that, 4 seconds, and it keeps on repeating itself, right? So 4 seconds and 4 seconds and so on, right? So in this case, my time period, or the new time period, is 4 plus 4, which is 8 seconds. And my frequency changes to be 1 by t, 1 by 8, that is 0.125 hertz, right? So now I have a new clock which has a divided frequency of it, which has a frequency which is less than 0.25 hertz. And then if you observe it carefully, by what factor has it reduced, or by what factor has the frequency gone down?
By half.
Right? So you are basically dividing your clock frequency by half. So whenever I say I'm dividing the clock, what I mean is I'm dividing the frequency. So this clock new is basically a half frequency clock of the original clock. And there are ways to do this. I mean, there are different methods to do this. And one such method is just employing a flip flop and feeding a clock into it. And say it's this is the clock that I'm feeding into a flip flop, right? And as we know that our flip flops perform at every positive edge. So if I have a very long construct written, or a very long code written, where I say at every positive edge I will flip the output that is coming out, right? So I'll say always at positive clock, reverse the output. So it'll stay in state 0 for 4 seconds, and then after 4 seconds it experiences a different positive edge, and at that state it changes to high state, and so on. It keeps on repeating itself. Does that make sense for everyone? Is that clear for everyone? It is really important that you understand this part of it, because the next version, or the next step for this is kind of dependent on this. If there is any confusion, do let me know. I will try to clarify it. Is it? Yeah, we'll get to the purpose of division, yes. But before we do that, do you understand what division is in general? We will get to why we are dividing the clock and everything. All right, since I have no questions, I'll assume you guys understood this. So now we'll understand one important concept, right? So in this case, in the case of division that we did earlier, what happened was, again, from this point to this point is one clock cycle. So you're waiting for one clock cycle to flip your signal, right? So for every clock cycle, you're trying to flip your signal. You can do something really similar, right? You can always say, I'll wait for 2 clock cycles and flip my signal, or I'll wait for 3 clock cycles and I'll flip my signal. And you have already had hardware or a piece of Verilog code that will basically tell you the number of number of edge or number of cycles of your clock, because that's what you have designed in your week one. So you try to design something which will flip, or which will try to give you a number for every clock edge that you're trying to generate. So what happens is, our board or the FPGA that we are using basically performs at 50 megahertz, right? So the clock that is present inside the board is basically 50 megahertz in frequency. So we want to construct a stopwatch that goes on, or it keeps changing, or it updates its output at every 1 second. So when I say 1 second, the frequency is basically 1 hertz. So what we want to do is, we want to convert this clock that is present at 50 megahertz inside the board to a 1 hertz clock. And the way we do it is using our clock division, or using, by counting the number of clock cycles that are present in it. And we'll try to find out at what clock levels, or at what number we are trying to change it. And that's the purpose of clock division in most of the cases. Like, we want either certain parts of our circuit to perform at different frequency, or you want your output to have work at a different frequency, or things like that. And because you have different needs for different parts of your circuit, you generally divide the circuit's frequency. Like, there is for example, when you construct an FFT, for example. So different, and FFTs, I'm pretty sure you're familiar with butterfly diagrams of FFTs. So different parts of the diagram need to happen at different frequencies, and because of which you actually come out with different versions of clocks. Give me 1 second. I have a question. Yeah, so there are two checkoffs for this lab. So if you are not able to get it checked off today, I will check off both the parts of the lab next week. And I'm pretty sure your whole lab is due towards the end. So we have 2 weeks to check off 2 weeks. So that should not be a problem. Yeah, don't worry about it. All right. So is everyone clear so far? Is everyone okay with this 50 megahertz to 1 hertz logic that we are trying to implement?
I had a quick question about it. Just there's also like a 10 megahertz clock that's in there. Can we use any of the clocks that are present?
So I'm pretty sure the default clock in it is 50 megahertz, but if you are able to generate a 10 megahertz clock, you can always use that. But again, you need to do a bit of different calculations to make the conversions. We'll get to the calculations part now.
Cool, thank you.
All right. So is this clear for everyone? All right. So what we'll understand is, we have our frequency to be 50 megahertz, right? So our time period essentially will be 1 by 50 megahertz, or 15 to 10 power 6, right? And this will give us some value, say suppose n seconds, right? So it'll say you have 50 megahertz clock, and the time period of that particular thing is certain value, right? So and we know that it is 0.2 into 10 power something. So if you do 0.02, because 1 by 50 is 0.02 into 10 power minus 6, or something like that. So these many number of seconds. And then if we do the time period of this particular 1 hertz clock, we say 1 by 1, which is 1 second. So we have 1 second of time. So what we need to understand is that inside this 1 second, right? So inside that particular 1 second that we are trying to generate, there are certain number of 0.02 seconds that are 0.02 into 10 power minus 6 seconds that are present, right? So the way we understand this, or the way we do it, is we say 1 second divided by 0.02 into 10 power minus 6, which will basically give us the number of cycles, or the number of repetitions of this particular frequency, or this particular clock cycles inside this 1 second cycle. Is this part clear for everyone? We'll get to why we are doing it, but do you guys understand the math so far?
Yeah.
All right. So now what we need to do is we need to go back to the previous diagram. And in this case, if you look at this particular clock that we are trying to divide, we waited for 1 clock period, and we said, okay, at every positive edge of that clock period, generate or flip your output. What we need to do in this new case is we need to divide this particular number that we get, that is the n that we get, and we say n by 2, and we need to wait for n by 2 number of cycles for this particular clock, in this clock. And after every n by 2 seconds, or n by 2 cycles, you need to flip the data, right? Does that make sense? Do you guys understand what we are trying to do here? So if we need to generate a clock, we need to generate a new clock which is of 1 hertz frequency, and that needs these many number of repetitions per time period. So this is per time period of the new 1 hertz clock. So this is the number of cycles of the old clock per time period of the new 1 hertz clock. And that time period basically consists of half of the time being low and half of the time being high. So that's the reason what we do is we split the total number of cycles to n by 2 and n by 2, and we say it is on for n by 2 and it is off for n by 2 time period. So we'll wait for n by 2 cycles, and we'll say the output is getting flipped. Does that make sense to everyone? Do you guys understand it?
Yeah, I think it's making sense.
All right. So I'm assuming you guys have some doubts about it. If you do, please let me know, because this is essentially the entire thing that you're trying to do. And if you don't have doubts, then great. You can actually proceed with the lab. So I'm assuming you have some questions, but we'll wait till anyone wants to ask them. But while they do, we'll get to this part quickly. So what we are trying to do here is we are trying to build a module which will basically have certain number of cycles stored here, for example n by 2, and this n by 2 cycles are constantly being compared to a number, say m. This number is nothing but the cycle count or the pause edge count of your base clock, that is your 50 megahertz clock. And whenever m is equal to n by 2, your output, say suppose your output is f, you say f is equal to inverse of f, right? Initially your f is initiated to 0, and whenever this cycle count is generated by the same counter design that you have used in your week 1, but instead of having the counter for 4 bits, you want to have it for n amount of bits, or you want to have it for certain amount of bits that can basically calculate, or that can basically accommodate the value n by 2. Say for example, if your n by 2 value is 10,000, right? So you want certain number of bits that can actually count till 10,000, because 4 bits can count to 1111, which is equal to 15, right? So you want something to count up till 10,000. So you want your counter that is present here to be of that width, and that counter keeps on counting your cycles until it reaches a value where you constantly keep comparing it to the value of n by 2, and whenever you hit the value of n by 2, you just flip your output, uh, and this particular flipped output or this particular signal is basically going to be the clock for the exact circuit you designed in week 1. So your week 1 circuit goes from 0 to 9 at any clock, and if you give it a 1 hertz clock, then that means you're basically having a design that goes from 0 to 9 and changes it every second. Does that make sense?
Yeah, I think so.
Yeah, so this is essentially your lab 4. This is what you want to design in your lab 4, and this is like basically what you want to do in week 2 as well as to complete your lab 4 part. So if anyone else has any questions, please let me know. It is kind of important for you to understand this lab because this is like the very fundamental thing for sequential circuits that you're trying to do. And I'll be here until 11 o'clock. And if anyone is ready to check off lab 4's week 1, then I'm more than happy to help them out.
So
Yeah.
I had a quick question
Sure.
on this. How do we get at the default clock in Verilog? Like, how do we? What's the
Oh, so you just in your Verilog you just give uh the input to be a 1-bit clock named clock, right? But when you actually implement it on the board, uh, that's when you actually have to. So if you go through your user manual, there should be a clock pin inside it, so you can actually connect the clock pin to certain inputs, and you want to connect this particular clock input to that pin when you put it on the board. But when you're using a test bench like a Verilog test bench or something, what you'll basically be doing is you'll be artificially generating a 50 megahertz clock. So for that, you need to again go back to this particular place where you say you're waiting for half of this time unit, and you say always at for half always for always pound half of this time clock is equal to clock inverse. So something like that. Does that make sense?
Yeah, that makes more sense. Thank you.
All right. So yeah, if anyone else has any questions, let me know, or else I'll start checking things off.
Yeah, I actually had a quick question. So for the
Sure.
week 1 stuff, I
Mhm.
kind of glossed over the way it was structured, I guess, so that like we can step it forward.
Mhm.
And I just built the one directly with the clock. So I already have it working where it's counting and I can stop it or restart it.
Oh yeah. That should be fine. That's actually what is needed from week 1. So for week 1, you should be able to start and stop wherever you want, and the clock that you're using for week 1 part should be an input, a physical input from you, so that I know that it goes at every positive edge or things like that. Does that make sense? Like you will be giving,
Oh,
you'll
gotcha.
be
Yeah.
changing the clock every time
So then I can just basically use exactly what I've got and just switch the clock in
to a
and
push
it should
button or
still
a
work.
slide switch. Yeah.
Okay, cool. Thanks.
Yeah. All right, let's see. I'm guessing you guys are. Yeah, that should be fine if you upload the recording today. Yeah. Yeah, I will be uploading this recording today as well. Yeah.
Did he attack her again?
Yes.
They both came out here and they seemed fine.
Because they both got scared of the water. They both ran
All right. I'll start off with
No, thank you.
Tom Poe if you're ready.
Yeah.
All right,
Um,
let's. You can share your screen, and then I'll look at your Verilog, and then I'll look at your test bench, and then your implementation on your board.
Okay. Can you see this?
All right. Yeah, I can. So let's see. You have a clock in, start, stop, reset, and display. That works perfectly fine. So you
Yeah.
have. Oh, is this the entire thing?
Yeah. Does that matter?
It should not be a problem. Let's see. So your
This
clock
is the
divider.
clock divider.
Okay, clock 1 hertz is called clock in. All right, that makes sense. Yeah, that should be fine. Let's see. Clock in.
And this is for the buttons.
Mm-hmm.
So when they assert low, they flip, and then they're complements of each other.
Sure, sure. Done. All right. Let's see the stopwatch logic. Your count. Oh, so this is your week 1 part basically. All right, that looks okay to me. Let's look at your test bench.
Yeah, and the test bench just has the clock, and then it asserts a few signals.
So it's not exhaustive.
So it
Okay.
like goes from every case, but I'm not sure if that is what you mean by exhaustive.
Yeah, I mean, if it goes through. So what do you mean by it goes through all the cases?
Like it'll go from like stop to reset, from start to reset, from start to stop, and it'll loop over all the numbers.
Mm-hmm. Oh, okay.
It's easier to see in the waveform too, I guess.
All right. So let's look at your waveform then.
Yeah, so this is basically with it in the base condition. So this would be like the display right here, 0.
Mm-hmm.
And then reset is high in this condition. And the start is so these are inverse. So it's kind of weird to look at, but this would be like
Oh yeah,
start.
that's fine. Yeah.
Start is asserted here, and then when reset drops off, it starts counting.
All right, keep going. Let me see if. Oh, okay. Is there a condition where after 9 it should basically go to 0? I think it is doing that.
Yeah,
All
so
right.
here it flips from 9 to 0.
All right. Let's look at your board then.
Okay.
All right. So what I want you to do is I want you to reset it to 0. And then just start it so that it is free flowing until 9. Yeah, we'll wait for 9 to happen. 8, 9, 0. All right. So reset it again, and then start it off. Start it off, and then stop at 4 seconds. All right. Start it. Start it again. Stop it, and then reset it now, and reset it back. All right. I think that's working fine. All right. That should be okay to me. Can I have your UID?
Yeah, it's U1228183.
All right, cool. All right, I think we are good.
Cool.
Is anyone else ready for checkout?